I'm going to start with some very brief overview of what I do, and then I will focus on one part of my work. So as Yorgo said, I'm working on the formal verification of AI systems. So the general problem here is that we have a multi-agent system, and then we have a safety specification. And generally, we model the multi-agent systems using some formal semantics, and the safety specification we're coding in a logic, in an appropriate logic. And then the aim is to check whether the property is entailed by the system. I mentioned multi-agent systems. The agents composing the system can be symbolic, can be neural agents, or they can be neural symbolic agents. One class of multi-agent system on which I focus a lot is that of what so-called parameterized multi-agent systems or agent swarms. So these are systems that are composed of an arbitrary number of homogeneous agents. So if you think about robot swarms, multi-party negotiation protocols, auctions, these are examples of parameterized systems. So here we would like to establish the correctness of the system for any number of agents in the system. This is in general an undecidable problem. And in my work, what I do is derive methods that compute some bounds on the number of agents that need to be considered. So reducing that infinite state verification problem essentially into a finite one. So here we identified multiple classes of systems which can be analyzed in that way. And we also derived methods for establishing the fault tolerance of the system. So in particular, computing the maximum ratio of faulty to non-faulty agents in the system before the protocol under analysis breaks. Another class of systems that I'm focusing on is neural symbolic systems. So these are closed loop systems where the agent takes input for the environment via a neural component, and the output of this neural component goes into a symbolic controller, which decides what action the agents take in the real world. So in this talk, I will focus on this component here on neural networks in isolations, standalone neural networks. And in particular, I will talk about the robustness, verifying the robustness of neural networks. Okay, so let me start with that. So I'll start with some motivation, why we need to verify robustness, and then I will focus on some of the key methods in establishing the robustness of neural networks. So assume here a neural network which performs a specific task. We train the network and then we evaluate it on a test set, and we found that the neural network performs really well. One key thing to remember here is that no matter how large the test set is, or whatever testing scheme we devise, we are always testing the network on a finite approximation of the environment. And what this means is that if we focus on a single test point, we'll find an area of essentially infinite other test points that we didn't consider. Now, why is this important? It is important because of the known fragility of networks to adversarial attacks. What is an adversarial attack? Is slight perturbations to a single test point for which the network gives a correct output, which, however, perturbation causes the network to give the wrong output. So this is an established fact, an established fragility, inherent fragility of neural networks. And these adversarial attacks are expected to happen in real time. And this is, of course, very problematic in safety-critical applications, because what it means is that the network, when deployed, it will not be robust to slight environment changes. So let me give some concrete examples where robustness comes into place. One example I mentioned here is runway detection, where we would like the model to be robust to different lighting conditions. Another example is credit default prediction, where we would like the model to be robust to variability, slight variabilities in the income, say, which should not affect the decision taken by the model. Okay, so this is the neural network robustness problem, and formal verification establishes the robustness of a neural network by checking a dense area of test points around a given point. So the whole area around a single point is considered. So this is, of course, an area containing an infinite number of test points, which, as I will discuss later, is what makes the neural network verification problem a hard problem to analyze. So here I give a graphical depiction of what a neural network verifier does. And I'm focusing here on the computer vision domain. Other domains, for example, tabular domain in finance are also analyzable using this approach. So we here take a single input, an image, and then we define an infinite set of perturbations of this image. This could be lighting adjustments like brightness, contrast. It could be random white noise. It could be geometric transformations. And finite representations of all these perturbations are given as input to the verification tool together with the neural network under analysis. And then the job of the verifier is to output robust if and only if every perturbation in the set considered causes the network to give the same output. So all perturbations are analyzed in the same way by the network. This is one possible output of the verifier. The other is to say that the model is not robust with respect to a set of perturbations, in which case it also gives as output the perturbation that violates the robustness of the neural network. Okay, so I will now start discussing how these output results are being generated, say whether a network is robust or not robust. And to do this, I will focus on neural networks with the ReLU activation function only. So this is verification methods on the ReLU function are the basis verification methods, which can be used to derive verification methods for other activation functions as well. So a quick reminder here on the ReLU function, this is a piecewise linear function. And what it outputs is that whenever its input is below 0, it outputs 0. And whenever its input is above 0, it outputs its input. So it has two linear segments. And given a set of perturbations in the input, we say that a certain ReLU unit is stable if it always operates in one of the linear segments. So it always outputs 0 or it always outputs its input. We say that the ReLU unit is unstable. Okay, so I will now talk about the key verification methods on establishing the robustness of neural networks. And they are all based on the concept of propagating bounds through the network. So what do I mean by this? We have as input in these methods lower and upper bounds for every dimension in the input of the neural network. So this is a hyper rectangle, essentially, which represents the area of perturbations that we consider. And then what we do is that we propagate this hyperrectangle through the network to derive some lower and upper bounds for the output of the network. Now, very, very crucially, because our network contains nonlinear functions, the ReLU functions, these lower and upper bounds, this output region that we derive will be another approximation of the actual output region of the network. Now, if this over approximations is contained entirely within the area defined by the output constraints that represent robustness, then we can conclude that the model is robust. Otherwise, we need to refine the over approximation, and I will briefly talk about how this refinement can be done later on in the talk. But now I will start talking about how we actually derive this output region. And to give an example of how this output region can be used to determine robustness in the classification task, say. So here is a simple neural network. These are the input and output bounds. And here we derive some lower and upper bounds for the output of the network. And based on these bounds, we can conclude that the network is robust in classifying the input as belonging to class 1, simply because the lower bound for class 1 is greater than the upper bound for class 2. Okay, so I will now talk about the propagation methods. I will briefly talk about 3 key methods of increasing complexity. And I will start with interval propagation. So this is the simplest, fastest method. And what it does is that it takes the lower and upper bounds for the network and then uses interval arithmetic to derive the bounds for the output of the network. So in this simple example that I have here, we have the lower and upper bounds for the input of the network. And then to derive the lower bound of the output, we take the weight here, which is -1. We multiply it by the upper bound here because the weight is negative. And then we add the product of the weight here times the lower bound because the weight here is positive. And this expression gives us a -2 for the lower bound of the network. Similarly, we can derive the upper bound of the networks as equaling 2. And now whenever we encounter a ReLU function, we simply clip the lower bound, the bounds computed so far by making the lower bound to equal 0. This is basically it. This is the interval propagation approach. It's super fast, as you can understand, but it is very, very imprecise. And it is imprecise because this type of propagation does not account for dependencies between the nodes in a layer. So what do I mean by this, by not accounting for dependencies? When we are using interval propagation and we are computing the lower bounds and upper bounds for a node, then what we often do is that we assume that a node at the input can attain its lower and upper bound at the same time. This, of course, can never happen, and it is what leads to significant over-approximations with interval propagation. So to give you a very trivial example to see how this happens, consider this lower and upper bound here, this region, where we subtract these bounds with themselves. Okay, so here we will expect the result to be 0. We will expect a lower and upper bound of 0. But because of how interval propagation works, the result will not be 0. Here we essentially use a computation which assumes that the node X here can attain its lower and upper bound at the same time. Okay, so this was interval bound propagation. Now I'm going to talk about symbolic interval propagation, which tries to alleviate this shortcoming of interval propagation. And this is achieved by propagating not concrete bounds, but symbolic equations through the network. So what do I mean by this is that we associate a symbolic variable with each input of the network. And then instead of propagating these concrete bounds, we propagate the variables and the symbolic equations derived by them. So here, as a lower bound, we will have -1 times x1 plus 1 times x2. And similar symbolic equation for the upper bound. And as for the ReLU function, again, is not linear, it's piecewise linear. So to propagate a symbolic equation through the ReLU function, the function needs to be linearly approximated. Here I show a linear approximation of the lower bound of the function. We can derive many equations for the lower bound. Basically, any slope of this line here will do. And there are methods of optimizing the slope that works best in deriving the tightest possible bounds in the output of the network. I will not focus in these methods on this talk. So this would be the linear approximation of the lower bound, and this will be the linear approximation of the upper bound. So again, at each step of the propagation, we have symbolic equations which depend on the variables that we assign to the input of the node. And from these equations, we can always derive concrete bounds by associating the input variables with their lower and upper bounds. And because every variable in the input appears only once in this symbolic equation, we no longer have the problem that we had before, that nodes at the input were attaining their lower and upper bounds at the same time. However, this does not happen variables in intermediate layers in the network. So we still have some more approximation in the output region that we derived from the network. It's not as significant, of course, as interval propagation, but there is still an over approximation. And this leads us to the third method I'd like to discuss, which is symbolic interval propagation with back substitution. These methods entirely alleviate the problem of nodes attaining their lower and upper bounds at the same time. And it is the most precise linear method that we have in deriving bounds for the network. How it works? Well, it works in a backward manner instead of forward manner. So that's the name back substitution. So concretely, assume we want to derive the bounds for these nodes here. We start with expressing the bounds for this node using symbolic equations over the variables of the previous layer. So this node here will be 1/2 times the symbolic variable for the previous layer from the previous layer. And then this variable here, we back substitute it with its symbolic equation over bounds from the even previous layer. And we continue doing this until we reach the input. And then we have that the symbolic equation for this node depends only on the input variables, in which case we can concretize these variables with their lower and upper bounds to derive concrete bounds for the node. Now, this is basically the method, and it amounts to essentially computing products of weight matrices in a backward manner through the network. This is, of course, much more expensive than the interval propagation method and the symbolic interval propagation method, but it is also far more precise. So if we were to compare these methods, the interval propagation method is the most efficient, but it is the less precise method, symbolic interval propagation. It's also very efficient, less efficient than interval propagation, but much more precise. And symbolic interval propagation with back substitution is much more precise, but much less efficient as well. It turns out that this is actually the key method that we want to use. And this is because these methods cannot be used to analyze even trivial networks. So even networks with only thousands of nodes, these methods are too imprecise for us to derive any conclusions for the networks. So this is really the key method, and there are a number of methods, some of which we developed safe intelligence, which focus on these methods, and they do not attempt to make it more precise because it's as precise as it can get essentially, but they try to make it more efficient. I will not focus on these methods in these talks, but yeah, I just wanted to highlight that this is a key method that we use in neural network verification. Okay, may I ask if there are any questions up to this point? Okay, so I will move on to branch and bound. As I previously said, the output region that we derive is another approximation of the actual region of the network. And this concretely means that we often cannot decide on the robustness of the network. In that case, we want to make the over approximation to reduce the over approximation so that we can decide whether the network is robust or not robust. And we do this in a branch and bound framework where we split the verification problem into sub-problems which are easier to analyze. Their analysis will be more precise. And the way this splitting is done is by two methods, really. One is by splitting an input dimension. So remember, we define for an input dimension a lower and an upper bound, and we can bisect essentially this range for an input dimension. And this will give us two different verification problems, each one corresponding to the lower or upper region of that bisection that we do. And because the range for the input dimension is smaller, the bounds that we derive at the output will be more precise. The over approximation will be less significant than it was before. The other way of branching or splitting is by splitting the ReLU function into its two linear segments. So we derive two verification problems here. One is where the ReLU function for a node that we chose, the heuristic of choosing the appropriate node to split. So in one branch, the node is always in the one linear segment where it computes, it outputs always 0. And the other branch, it's always in the other linear segment where it outputs its input. And we continue doing so until the approximation that we have at the output region is entirely contained within the output constraint defining what it means to be robust or safe. Now, this branch and bound framework is very popular in neural network verification. It has also very efficient GPU implementations. And the GPU implementations have helped a lot in scaling neural network verification to larger and larger models. And yeah, as I said, it's very, very, very commonly used, but it has one drawback. And the drawback that it has is that it's not easy to account for complex dependencies between neurons in a neural network. And these complex dependencies are being accounted by other methods that are that are used now in neural network verification, and I'm talking in particular about mixed integer linear programming. A quick reminder: what is mixed integer linear programming? A mixed integer linear programming is an optimization problem where we have a linear objective function which is sought to be maximized or minimized with respect to constraints over real valued and integer variables. And what we can do is that we can represent the verification problem precisely, exactly as a mixed integer linear program. And what we will have with this mixed integer linear encoding is that the verification problem will be satisfied. That is, the network will be robust if and only if the mixed integer linear program has no feasible solution. Here I do show the encoding of a single rail function. I will not talk about it in detail. I will only mention that the integer variables are used to encode the piecewise linearity of the rail function. We in particular use binary variables to encode that piecewise linearity. Now, how mixed integer linear programs are being solved is again a branch and bound framework where we branch on the binary variables encoding the piecewise linearities. And this branching, it of course creates an exponential search page in the number of rail nodes in the network. And it is what makes neural network verification a hard problem. It is in particular an NP-complete problem. But it turns out that state-of-the-art mixed integer linear solvers perform really well on the neural network verification problem. Say solvers like Groby are extremely efficient in analyzing the verification problems. But still, they are general purpose solvers. So fine-tuning them in a way to the neural network verification problem can further speed up the time it requires for them to solve a given problem. And I will briefly talk about some methods of speeding mixed integer linear programming. And these methods use the concept of dependencies between nodes. So here, what do I mean by dependency? We say that an unstable node, that is a ReLU node, which can be in either of its two linear segments, given a range of inputs, so the hyper rectangle that we had. So this node is set to depend on another unstable node. If whenever the other becomes stable, then the node in consideration becomes stable as well. And what this means in practice is that assume we have a method of computing this type of dependencies, and then assume that we establish that node R here depends on node Q. So whenever Q becomes stable, then becomes stable as well. And assume we branch, so we consider both its inactive and active branches, and then we go to the inactive branch. There, one of the branches of node R becomes stable as well. And we have there are some very efficient methods of computing these dependencies between the nodes in the network, which are then added as constraints to the mixed integer linear program being solved, or are used as heuristics to split the mixed integer linear program into smaller programs that are more efficient and so these were the key methods that I wanted to discuss. I will now move to some applications. I just wanted to ask at this point if there are any questions. Okay, so I will briefly talk one use case that that we worked on, safe intelligence, and this is work that we did with Boeing, and it concerns aircraft pose estimation. Boeing built some models which, as part of the so-called perspective endpoint methods, which analyze correspondences between 3D coordinates in the real world with their two-dimensional projections. And these two-dimensional projections are being computed using neural networks. So we analyze these models that compute the two-dimensional projections. And Boeing was interested in several things, actually, regarding the robustness of the models. Let me first talk about how the models work. So the models take as input an image of the runway, and then they output a set of key points in this image. And here what we like is that these key points do not change with perturbations applied to this image. And the perturbations that we analyze is random noise. So what I mean by this, some pixels change their value randomly, but slightly only, so that the final result is still the same image, which should be interpreted in the same way. That is, the key points should not change. We also consider photometric transformations, so the image becomes brighter or darker, and also geometric transformations. So these are transformations that capture geometric changes on the sensors so that the image is rotated, is translated, and so on. Now, the verification roadmap that we consider in this analysis, and the verification roadmap that we consider in most use cases, actually, is the following. So first, we start with simplifying the model and the input size of the model as much as possible. This is very important because again, the efficiency of formal verifiers with respect to the input size and drops exponentially. So the smaller the model, the better it is for neural network verifiers. And what we often find by working on real-world models is that the models can actually be simplified without hindering performance much. So what we typically do is that we work with the model designers to simplify the model as much as possible. Then this is followed by tuning and performance enhancements on the verifier. There are a number of hyperparameters in the neural network verifier itself, which can be tuned to specific models being analyzed. This often helps a lot with the performance of the verifier. And then we do analyze the model by deriving robust models. So instead of computing accuracy, we compute the so-called robust accuracy of the model. So this concerns the model not only being accurate in its prediction, but also be robustly accurate. So, so for every image that it outputs the correct prediction, the prediction remains robust with respect to the perturbations applied to that image. And let me highlight here and stress that this sort of analysis is very different from testing. In that it gives a lower bound on the robust accuracy of the model by being complete. So by complete, I mean the formal verification is always able to say whether the model is robust or not with respect to an infinite set of inputs. Whereas testing, it can never analyze all those inputs, so it always gives an upper bound to robustness. So an upper bound concretely means a false sense of confidence in the robustness of the model, essentially. Here I show some of the results that we derive from the model. And these are typical results that we find in the analysis of real-world models. Let me first say that, as you can see here, the images that we consider are grayscale. So this is part of the simplification that we did for the model. We started with very high resolution images, and then we consider grayscale images and downscale the images without dropping the accuracy of the model. And what we find is that with very, very small perturbations, the model can be robust. But then if we slightly increase the perturbation range, the model starts becoming very fragile. And it becomes very fragile in perturbation ranges for which the images from the perturbations causing the network to misclassify, they are semantically the same. They are imperceptible, essentially, at least to the human eye. And the conclusion here is, of course, these models are always problematic when being deployed in the real world. Okay, so significant progress has been made in scaling up neural network verifiers. And we reach the point where we conclude we can do sound and complete analysis of networks of up to millions of ReLU nodes. But still, formal verification is not scalable to the even larger models that can be found in the industry today. So I will now talk very briefly about one of the latest methods that we developed that appeared in NeurIPS this year, which tries to overcome this scalability limitation of formal verification. So for these methods, instead of talking about robustness verification, we talk about robustness validation, and I will explain why we use validation instead of verification. So very briefly, the method is a global optimization method. So this is a black box method. It doesn't analyze the internals of the neural network, so it doesn't use its weights in any part of the analysis to derive a result. And it adopts, as I said, a global optimization method where it considers increasingly tighter intervals at the input, for which it uses an estimation of the Lipschitz constant for the function to derive a lower bound for that interval. And it iteratively selects the interval with the lower lowest bound, which it further refines into tighter intervals for which it computes lower bounds, and it continues so on and so on until an optimization budget is reached. Now, if this Lipschitz constant is an upper bound for the actual Lipschitz constant of the network, then the method is sound and complete. However, computing tight Lipschitz bounds is in itself a very hard problem. It's a computational intensive problem, and thus, by computing the tight Lipschitz bounds, we cannot essentially speed up the analysis as we want to do. Of course, very loose Lipschitz bounds can be computed effectively, but loose bounds cause the method itself to operate in much more slowly. So what we do here is that we compute estimations of the Lipschitz constant. And this means that the Lipschitz constant can at times not be a sound upper bound of the actual Lipschitz constant of the network, which may cause, theoretically, then the method to output robust when the model is not robust. So this is the reason we say validation and not verification, because theoretically, this can be an unsound method. But in practice, and with some practical enhancement that we implemented, the method never output a wrong result. And we tested this on benchmarks for which we know the ground truth. And we had 0 false results when state-of-the-art verifiers, sound and complete verifiers, had wrong results on these benchmarks. Why they had wrong results, the sound and complete verifiers, theoretically they are sound and complete, but implementationally they may have errors. And these methods enable us to scale up significantly robustness analysis. We went up to models with 300 million tunable parameters, and it was the first time we've been able to analyze vision transformers with very large input sizes. I'm concluding the talk here, and just to briefly say that there are some topics that related topics that I didn't talk about, but are very, very relevant. One is certified learning. So, as I mentioned, formal verification establishes whether or not the a model is robust or not to input perturbations, and this is always important to know. But in the case that it is not robust, then what do we do? So the overall aim is to, of course, have a robust model. And certified learning is a method of improving the robustness of neural networks by adjusting the objective function during learning to account for adversarial perturbers trying to cause the network to misclassify. I also haven't talked about tree-based models, so decision trees, XGBoost models, ensembles of decision trees, and so on. These are also very fragile to adversarial perturbations. And here we have different verification methods for their analysis, and also methods for robustly training decision trees. Now, to conclude, formal verification for AI, it's a relatively new area of research. It really started in 2018, and there has been significant progress since then. In 2018, we've been able to analyze only models with hundreds of nodes. Now we can easily do hundreds of millions. And it's increasingly proving a useful analysis tools for AI systems. Scalability is still an issue that is continually being worked on, and we do have significant progress here. But I think very, very importantly, in establishing the safety and robustness of models is not simply to scale up verification methods, but also to train models so that they can be easily verifiable. And we often think that this is, to some extent, possible without significantly hindering the performance of the models.